Let's continue the discussion of what the derivatives of a function tell us about the graph of a function, how a function behaves graphically. So let's start exploring what the second derivative actually tells us about a graph. So remember, if the derivative is telling us about the slopes of the tangent lines of a function, then the second derivative is telling us about how those slopes are changing. So we already know how to figure out where we've got intervals of increase and decrease, and now we're going to talk about a concept called concavity. So if we have a function and it's defined on some interval on which it is differentiable, we'll call that interval I, we call the function concave up if the slopes of the tangent lines are increasing. If the slopes of the tangent lines are increasing, that means that the second derivative is positive, because that means the rate of change of the first derivative is positive. So when we talk about slopes increasing, I just grabbed a ruler for those of us that are visual learners. And if we take that ruler and we take a look at this particular curve that I have drawn here, and I drew in some of the tangent lines, but you can see here we have a fairly steep negative slope, but then it gets less steep, so it's actually increasing. The slope is increasing, and then it gets even less steep. At some point in here, it hits 0, and then it goes positive and continues to increase. So this is an example of a concave up curve. Graphically, it would look like this, and the second derivative would be positive because the slopes of the tangent lines are increasing. First derivative is increasing. That's what that means. When we say the slopes of the tangent lines are increasing, that is saying that the slopes, that the first derivative, f prime of x, is increasing. So we are actually looking at the second derivative, f double prime of x, and it's giving us info about the first derivative changing. Okay, it gives us information about how the first derivative is changing. So f prime of x is increasing when the second derivative is positive or greater than 0. Okay? That's what that's saying there. And then graphically we've got this this picture. This is called concave up. So the slopes of the tangent lines are increasing, and if the slopes of the tangent lines are increasing, visually there's a couple of ways that you could think of it, that the function is actually sitting on top of its tangent lines. So if you were to draw in the tangent lines and the function were sitting on top of it, that would be a concave up curve. Another way to think of it, if you were to pour water, if you think of, water pouring down from the top of the screen. If water is pouring down from the top of the screen here, and the actual curvature would hold water, okay, as it would sort of fill in down here. If it would hold water, we say that that is a concave curve. So there's a couple ways to look at it visually. Mathematically, though, the slopes of the tangent lines are increasing. That's what we call concave up. Okay, let's take a look at concave down. So concave down, and I notice I have a typo actually right here. Concave down, we say a function is concave down. Zoom in a little bit there. We say that a function is concave down if the slopes of the tangent lines are decreasing. So let me grab my ruler again. So if the slopes of the tangent lines are decreasing, so notice here we have a positive slope on this particular curve, and if we continue and we kind of just trace out those tangent lines as we go, notice it's getting less steep. The slope is decreasing, and at some point it hits a 0 in here, horizontal tangent line, and then it even goes negative, and it continues to get more negative, more steep, more negative as it gets steeper in this direction. So concave down if the slopes of the tangent lines are decreasing. And if the slopes of the tangent lines are decreasing, that means that the second derivative is negative. So again, kind of back to what we're talking about when we talk about the slopes of the tangent lines decreasing. So f double prime of x gives us information, as we talked about up here. F double prime of x is giving us info about f prime of x changing. So f prime of x is decreasing when the second derivative is less than 0, when it's negative. When the second derivative is negative, that's an indication that the first derivative is decreasing. Slopes of the tangent lines are decreasing. Okay. So we've got the visual, we've got the definition of concave up, concave down. Oh, and then in terms of what does it mean in terms of a visual? So if the tangent line actually hangs, if the curve actually hangs from its tangent lines, so you see here it's just sort of hanging underneath the tangent lines, that is an indication that we are concave down. If it's hanging off of its tangent lines, if you draw on the tangent lines and the curve is hanging from them rather than sitting on top of them. Okay, and another visual is if you pour water from the top of the curve and rather than holding the water, it just kind of spills off and it would spill off of this curve. So there's kind of another visual, another way to think of concave down. If water were to be pouring from the top of your paper or the top of the screen and it were to be just spilling off of the curve, that's concave down. Or if you were to draw on the tangent lines and the curve is just hanging from its tangent lines, that would mean that it's a concave down curve. So those are some visuals there. Okay, so that's what it means to be concave down. Where the concavity changes is what we call an inflection point. Put that on the screen. So when we have a curve and we have a change in the concavity, that's what defines what we call an inflection point. So it doesn't matter, it could be going from concave down to concave up, or it could be going from concave up to concave down. On the graph that I have here, we have a single inflection point right here where the curve is changing concavity. So again, notice that this on this side, as those tangent lines are decreasing, we have concave down, and then as the tangent lines are increasing on this side of the curve, we have concave up. So I indicated that with the up and the down, concave up to concave down. And at the point at which they change, we call that the inflection point. It's a point where the concavity changes. Okay, so let's take a minute and look at the graph actually that we looked in the previous video, but this time I want to look at it for concavity rather than for intervals of increase and decrease. So I'll pull that up on the screen. Okay, so here is the graph that we looked at last time. We took this graph, it was a graph of a function, y equals f of x, and we figured out where was it increasing, where was it decreasing, stated those intervals, and stated the local maxes and the mins. So I want to do the same thing. I just took a copy of it, and I want to say, let's use that same graph, but this time, let's look at it not for intervals of increase, decrease, let's look at it for the intervals of concave up and concave down. So where is this function going to be concave up? Where is it going to be concave down? And where, oh, I didn't write it, but actually let's find the inflection points too. So let's find IP for inflection points. Inflection points. I guess it's the first time I've used that abbreviation. So inflection points. So let's look for those inflection points. So notice on this curve that we are concave down in the first interval. We're concave down. The slopes, if we were to take our ruler, the slopes of those tangents start out very steep and then they get less steep. They are decreasing. In fact, they go to 0 and then they even go negative. Right? And they go negative, and then right in here, they kind of hit a peak of steepness, and then all of a sudden there's a little change. And now they start to get more positive, right? They go from being very steep negative, and then all of a sudden they start to increase. Rather than decreasing, they start to increase. And they keep going. And you can kind of visualize that as we go. They keep going. They get steep, 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 steeper, steeper, steeper. And right at x equals 4, we hit sort of the max of the steepness, right? We hit a point right here where we're very steep at our tangent lines. And all of a sudden they start to decrease. They start to get less steep. And they get less steep, less steep, less steep till they hit a 0. And then they start to get steeper again. They start to increase again. So taking all of that, and I know that was with the ruler and it's kind of hard to see that on the screen, but taking all of that, what we have is an inflection point right here at 1. And on this first little interval, if we're going to write concave, let's do our concave up and our concave down. On the first interval here, we are actually concave down. So from 0 until we get to that inflection point at 2 where there was that switch, we're concave down. Then, as we continue to go, oh, and then the other thing you could think of too, and I'd mentioned this before, let me erase the highlighter. You could also think of drawing in your tangent lines. If you draw in some tangent lines here, you can see that this curve would be hanging off of its tangent lines. It's concave down, or if we were to pour water, it would be spilling off of the curve on that section. Versus after that inflection point, when we start to draw our tangent lines, the curve is actually sitting on top of its tangent line. So that's another way to see it. The slopes of the tangent lines are increasing. So it was down in this little portion, and now on this next portion, from here until we get up to that point right there, we are concave up. So from 2 to 4. And again, these are open intervals because right at those inflection points, there's a moment at those inflection points where the second derivative is actually equal to 0, and it is neither positive nor negative. It's similar to the way we talk about the critical points for the first derivative. We'll actually talk about these points as our second order critical points, places where the concavity could change. Not that it does, but it could change. Not that it always does, but it could change. All right, so we're concave up from 2 to 4. And then let's continue. Then we go concave down on this little piece. And so we're concave down from 4 to 5. So it's going to be hard to write that in there, but I'll write concave down on that little segment. And then from 5 to 7, we are back to being concave up. So from 5 to 7, we are concave up. And since the concavity switched, this point at x equals 5 is also an inflection point. So our inflection points are occurring when x is equal to 2, 4, let's grab them from the graph, and 5. And if we wanted to write those as ordered pairs, that would be at the point, so x equals 2 would give me the ordered pair 2, 2. 4 would be the ordered pair 4, 3. Just pulling those from the graph of the function using the function's value, which is 5, 4. So those are our inflection points, not intervals. I know intervals and ordered pairs, when we use them in the same problem, I don't want you guys to get confused by those. These are the ordered pairs, the points where we have those inflections. Okay. All right, so all of that tells us about the concavity. And because on the very next example, I want to go through a process where we use sign charts, let's just go ahead, just like we did over here, where we use that information to talk about the increase and the decrease and pull that information in to give us a sense of what the graph looks like. I want to do the same thing for the concavity. I want to create a sign chart for the second derivative. So let's make a sign chart for the second derivative of the function, because that tells us about concavity. Tells us about concavity and inflection points. So if we were to make, I'm going to actually zoom out and get just the information that we have here. Not even look at the graph, just this information, because that's what we're going to end up having. We're not going to have the graphs to start with most of the time. What we're going to have is we're going to have a function which we can take its first and second derivative and generate sign charts. So what if we knew, when we took the sine of f double prime of x, let's talk about that, and information that tells us information about concave up and concave down. Now this particular function we're looking at from 0 to 7. We know that these are the potential places, right? We actually do know their inflection points because we have the graph, but let's just say we didn't know that yet. And we knew that we had 2, Actually, I'm going to make 2 a little bit further out. 2, 4, and 5. Okay? And then we knew that we were concave up from 2 to 4 and 5 to 7. That means the second derivative is positive. And we knew we were concave down. So that means the second derivative, the sign of the second derivative is negative. Since each of these points has a change in concavity, that makes each one of these an inflection point. Each one of those is an inflection point. And now we can pull all of that in because of the change in concavity. Now, if the concavity did not change, then these would not be inflection points. But the concavity did change, so these are inflection points. It went from down to up to down to up. So those definitely make those inflection points, and we can see that on the graph. And now we have all this information that together with this information, we could also put all this information together on a graph. If we have both of our sign charts, we could put all the information together and it would give us a very clear picture of the graph if we didn't already have the graph, which in this case we did have the graph. But notice on the little sketch that I had in here, we would know that at 2, notice we would normally stack these sign charts one on top of the other so that we could see the 2, the 4, and the 5 as well. But notice that we know that right here we have an inflection point, so we could add this into the graph. We would also know somewhere in here at 4, and again, this is our rough sketch, but we would have an inflection point here, and we would know that this point right here is an inflection point. So we could add those pieces into our rough sketch of the graph if we didn't already have the graph. Okay, we're going to use that, and we're going to actually have a process by which we determine concavity and inflections that's very similar, very, very similar, except for using the second derivative, to what we do to figure out where we have intervals of increase, decrease, and our local maxes and mins. Okay, so here's our test to determine the concavity and the inflection points. And it should seem similar because, like I said, it's very similar to the test that we use to determine intervals of increase, decrease, and our local maxes and mins. Except this time, we're going to take the second derivative, because the second derivative is what tells us about concavity. So we're going to take the second derivative and what we're going to call second order critical points. So the second order critical points are simply where the second derivative equals 0 or is undefined. That's going to generate a list of numbers, a list of values within the domain or the interval that we're looking at. And we're going to use those numbers to break up the number line or the domain. So whatever the domain is or whatever the restriction, if we have a restricted interval, whatever the interval we're looking at, we're going to break it up. We're going to drop those second order critical points on the number line to break it up into intervals, and then we're going to test the sign of the second derivative. So the sign of the second derivative is what's telling us if we have concave, it's telling us about the concavity, telling us if that on that interval we're concave up or concave down. So we make a nice little sign chart, we just test the second derivative to figure out if it's positive or negative on each of the intervals that are created by those second order critical points, and that will tell us about concavity. Then the inflection points simply come from where we have changes in concavity. So the inflection points are just wherever there is a change in the concavity. So this is the process that we're going to use for finding, I'll erase all my notes here. This is the process that we're going to use to find our concavity and our inflection points. So make sure you take a moment and freeze the screen here and take down this process. This is the process we're going to use. And again, it should feel similar to what we did for with the first derivative to figure out intervals of increase, decrease, and the maxes, local maxes and mins. Okay, so this is an example that we did on the last video, and I want to continue with the same example because when we come across a function, we're going to want to know where it increases, decreases, where it has local maxes and mins, but we're also going to want to know what the concavity is and on which intervals we're concave up, concave down, and where those changes occur, those inflection points are. So I'm going to take this same function that we already have all this information about, and I'm going to continue the same function, and I'm going to find now where the concavity is. So let's take this function, and I just copied it over here, And now let's determine the intervals of concave up, concave down, and the inflection points. So I copied the function down, here's the function, here's the first derivative. Now we're going to take the second derivative. And when we're done, we'll look back. The process is going to be very much the same. Remember what we did here. We found the critical points. We created a sign chart for the first derivative, and that told us about where it increases and decreases. Now we're just going to do the exact same thing, but with the second derivative. So we're going to take the second derivative here. We get 36x squared minus 48x minus 36. And now we need to find the second. So now we need to find the second order critical points. So we need to figure out where is f double prime of x equal to 0 or undefined. Now, by the way, this is a polynomial. Therefore, each of the derivatives is also a polynomial, and therefore this polynomial of the second derivative is never undefined. So this is never undefined. So just kind of cross it off like it's not undefined. Okay, that's what that cross off means. I'll write this. It's a polynomial. So it's never undefined. But it could be equal to 0. So let's figure out, is the second derivative ever equal to 0? So 36x squared minus 48x minus 36, is that ever equal to 0? Let's see, I see a common factor of 12. And that's not going to factor, so let's just jump to the quadratic formula. So x would be 4 plus or minus the square root of 16 minus 4 times 3 times negative 3 all over 6. And so that would be 16, so that's going to be 52. And over 6. Double checking my math there. So then that's going to be 4 plus or minus, that's 4 times 13, so 2 root 13 over 6. And so this would be 2 plus or minus root 13 over 3. And so that gives me the positive root there, gives me 1.87. And the reason I'm going to approximate here, so that's the positive root and negative 0.54. So that was 2 plus root 13 over 3, and this was 2 minus root 13 over 3. Now, the reason I did that is because we're going to create a sign chart now, and I want to know kind of whereabouts those should go. So now we're going to go ahead and create our sign chart. I was going to put it under the other one, but I think it's going to get too messy if we go back over there. So normally we would do these all together. We do the first derivative sign chart, and then we do the second derivative sign chart, and we could stack them right on top of each other, but or right one under the other so that we could really see all the information. But I'm not going to do that here. This is actually from infinity, negative infinity to infinity. Meant to mention that up here. We talked about it in the first derivative, but the domain here is all reals and there's no restrictions on that domain. So if we had a restricted domain, then we would only look at the sign chart on that restriction. But this is from negative infinity to infinity. It's the x-axis, or kind of an abbreviated rectangular coordinate system where we only look at the horizontal axis for right now to give us information about the graph. And we're going to look at the sign of, this time, the second derivative. So we're looking at the sign of the second derivative to give us info about concavity. So where is this concave up and concave down? So the 2 points that we have, and I'm going to put their decimal approximation here. When we go and we write the intervals, we'll use their exact values, but for now we'll put the decimal approximation. I guess underneath I could put which is equal to, and 2 plus root 13, which was 1.87. So 2 plus root 13 over 3. Okay, And I think it's worth having those. We'll just circle those. Those are the exact values, but in order to pick test points and stuff, it helps to have the decimal approximation. Because remember, we're going to pick a test point. So now we just pick a little test point. So we pick a test point, something to the left, and where is my second derivative? There it is. There's my second derivative right there. We're going to test into the second derivative. Now we don't have the factored form, but we can still test just the signs without looking at the exact values. Maybe you pull out your calculator and do the exact values. But I think it's useful just to kind of get a good to get good practice just looking for the signs, right? A number sense, as your numeracy is a little bit stronger, the faster these sign charts can be. So we're going to pick something to the left of negative 0.54, which is 2 minus root 13 over 3. Like, I don't know. I'm going to grab negative 5. Like, let's just think negative 5. So I think about negative 5. I think about plugging it in here. 3 times negative 5 squared is going to be 75. Then I'm going to add 20, and then I'm going to subtract 3. That is going to be positive. So that's concave up. Okay? If you want to actually test a number in there, go ahead. Then I'm going to pick 0 because 0 is always an easy one to plug in. If I plug 0 in here, oh, and by the way, we're also multiplying it by 12, but that does not change the sign. If I plug 0 in here, I'm going to have 12, which is positive, times a negative 3. So that's definitely a negative. I know it switched, it went from up to down, but do not make that assumption. On these sign charts, it is not always the case that your concavity or your intervals of increase, decrease, that the signs of your first derivative or second derivative will always switch. So don't always make that assumption, just test your points. Let's try something like a positive 5 in this last interval. If I plug in a positive 5, we're going to end up with, again, 12, which is positive, so that doesn't change anything. We end up with 75 minus 20, give me 55. That's going to be positive as well. So we definitely have concave up on that interval, which makes these points inflection points. So this is definitely an inflection point because there's a change in the concavity, and this is an inflection point because there's a change in the concavity. So we know that that's an inflection point, and we know that that is an inflection point. So when we go to summarize this, so the summary here, the summary is that we have concavity. We can talk about the intervals of concavity. So we are concave up, concave down, and we'll write these as the open intervals. So we are concave up from negative infinity. Remember that this was across the entire number line. So from negative infinity to 2 minus root 13 over 3. And I will write in the exact value there. Then we're also concave up from 2 plus root 13 over 3 to positive infinity. And we're concave down in between. So 2 minus root 13 over 3 to 2 plus root 13 over 3 is where we're concave down. And we have inflection points at x equals 2, and I'm going to go ahead and summarize this with the plus or minus, 2 plus or minus root 13 over 3. If we wanted the y values, we could plug those into the function, but in the essence of time, I'm going to stop right there. We could get the approximation and plug those back into the original function. But I just want to come over here, and I want to go back to, I know it's hard to get this all on the screen at the same time, but I wanted to just come back over here to this rough rudimentary sketch that we had right here. And if we could stack what we just did underneath it, and we could see that negative, remember we actually have an inflection point at this point, negative, it was negative 0.54 and at 1.87. So, we actually have inflection points right here and right here. And if we had stacked those two sign charts on top of each other, or one on top, one on bottom, we could then see that we would have inflection points somewhere in here and somewhere in here. And again, this is a rough sketch, but when we put our two sign charts together, we get a really clear picture of what the function looks like. And then we can plug the x values for the maxes, mins, and inflection points back into the function to get ordered pairs. And we're going to have a very accurate graph without ever having to go to a graphing calculator. We would have a very accurate graph and see a really good picture of the function. And so we can see all of that information, using the first and the second derivative. It gives us just loads and loads of information about the function. So I'm going to end right here. I'll leave this on the screen, this last example that we did. And we did it with a polynomial. And polynomials behave really nicely. They're nice, smooth curves, continuous, and all of that. So we'll come back and we'll talk about some more examples in later videos. But this is the general idea of this section, that we take our first derivative, we take our second derivative, and we can generate all this information about function behavior, increase, decrease, concavity, maxes, mins, and inflection points.